Thank you for having me. I'm Tesla DuBois. I have to admit right off the bat that I think I might be in the wrong place. I have never taken a cartography class. I definitely have never taught one. But I love maps, and so I submitted to present this because I wanted my work to pay for me to come here so I could be around other people who make maps, and it worked. I just hope that now that I'm here, you find this at least interesting. Maybe not useful. So, a little bit of background to this. I work at the Consortium for Policy Research and Education, which is housed at the Graduate School of Education at University of Pennsylvania. We're a pretty small office doing education research. And I'm a research specialist, so I basically mostly do what other people tell me to do, which is a lot of different things, but I really like maps, and I'm really interested in integrating maps into the work that we do at CPRE. And so I've been taking some classes here and there, and trying to convince people that this is really worthwhile. And you all know it's worthwhile, which is why you're the wrong audience, and you also have way more experience than me. But anyway, I created this project that I intended to show to my fellow researchers, the ones who actually are going after the grants and designing the whole thing, to try and implore them to incorporate some spatial analysis into the education research that they're already doing. So, if I can find... Sorry, I don't know where my mouse is. Enter. Here we go. Okay, so my debut at CPRE with spatial analysis was that I tacked on a little bit, just a tiny little map that showed up in this report from a much larger project that was looking at discipline in Philadelphia schools in K through 5, grades K through 5. So the school district of Philadelphia had adopted a new code of conduct, and they weren't exactly sure how this was being implemented in the schools, and so they had us go in and do mostly a lot of qualitative work looking at how discipline actually unfolds in schools. And from that, we created 3 profiles, and all I did was map the profiles and then put some demographic information underneath it, and we actually saw some statistically significant clustering of the profiles, which you would think, you wouldn't really expect, and also some seeming relationship with the demographics. So I decided to take that and run with it a little bit. In this, of course, we had to make some pie charts because we couldn't identify which schools were which profile. So this is some aggregated data by the network. We have networks in Philadelphia. I still need my mouse. Does anybody know how I can get my mouse back here? Control. Hang on, because I'm gonna have to click on something. You feel free to come up and take over if you think you can help me here.
So we can see your mouse pointer.
You can? Oh, that's good.
So if you move it down and click on something.
Oh, okay, good. All right. Then I just have to use that. Okay. All right, so we're diving in here to a little Esri map story that I made, and I'm going to try and fly through this. So basically, I was trying to answer the question about whether we can account for variation at the school level by looking at community level attributes. And so we have several different kinds of predictors that we're eventually going to use in a regression model. And so most of this is just about how do we aggregate things that are happening in neighborhoods to the school level so that we can then run a regression. I have several different data sets that I'm looking at. This one, oh, you're not seeing what I'm seeing anymore. Sorry, guys. You missed a lot of good stuff. No? Not what you... This is not the website. Let me take it out of presenter mode. That'll help. End show. Okay. Here we go. Here. Are we there? Yeah, we're there. Okay. So we have several predictors. I generated a data set that was nonprofits that have youth in the description that were listed on idealist.org in 2016. This was because there's some research that suggests that students who have role models and mentors in school, that impacts their behavior. So I was wondering if that could extend to the outside community. So I was looking for places where students might engage with mentors or role models outside of school. So we have nonprofit organizations who have youth in their description, out of school time, police, athletic league, libraries. I'm just clicking through these so you can appreciate kind of the distribution. Libraries is notably the most uniformly or dispersed distribution here. We have CDCs, which I don't know where you're from, but they're kind of a big deal in Philly. Boys and girls clubs and YMCA branches. I also thought students might find mentors in religious congregations. So we have churches, they're kind of all over the place. This mimics a little bit population density with Center City down there, if you're not familiar. Synagogues and mosques, which I thought the contrast of those two were pretty interesting. And then I just have some demographic data, so educational attainment. This is where I start to get really nervous about who's in the audience, because don't judge my color schemes. I don't know what I'm doing. I know specifically that one's wrong because the darker green are actually the poorer people. So single moms is actually percentage of females being the leaders of households with minors. It's not only mothers being the relationship. Anyway, moving right along, we have crime data, a selection of crime data. And this is where, to me, it gets interesting. So I'm thinking about how to aggregate this data to the school level. And that was kind of the exercise for me in doing this. So I experimented with a quarter-mile buffer, but there's a lot of crime, for instance, that's outside of the quarter-mile buffer, half-mile buffer. Then when you zoom in, these buffers overlap, and then you're going to be counting the same crime event towards multiple schools, so that doesn't work. And then for something like CDCs, you could take an average nearest neighbor, and if we did that, and then here we have the larger points are representing schools that are closer to CDCs. Anyway, what I came down to was that it's really dependent on our hypothesis. This is really my hypothesis. I say we. The only other person involved with this was my infant daughter. I started this when I was 9 months pregnant and ended when she was 2 months old, so she was by my side the entire time. That's the we here. Anyway, so my hypothesis is really that students are impacted by things that are happening around their homes, not that they're hanging out around school all the time. So I ended up going with catchment areas, which we have in Philadelphia. So there's definitely some drawbacks to this because what happens, say, a crime event that happens here might impact a student over here more than a student over here, or like there's nothing about a catchment area for a school that's going to keep them from going to a YMCA right on the other side of it. So it is what it is. But that's what I went with to aggregate all of my data. Now for the census data, this was another thing that I needed to think through. So we have catchment areas and census tracts. They clearly don't line up. I experimented with using the centroid of each and then saying centroid of the census tract, and then attribute that census tract's data to the catchment that the centroid was within. Like that, you can kind of see how it lines up. They're not bad in some cases, but in some cases you get some funky things going on. So what I ended up doing instead was looking at the cross-section of catchment and census and creating, using like just cutting tool to create unique segments. And then my projections may have led me astray here, but I measured the geometry of each of these and then weighted the census tracts so that I could attribute the portion of the census tract that was in the catchment to, like if there's 12, you guys know what I mean, and then attribute that to the census tract so that we're not double counting single mother households, and that, everything hopefully gets distributed correctly. So now I'm looking at out-of-school suspensions. My rate of out-of-school suspensions could be contended with by people of the School District of Philadelphia because it doesn't account for repeat offenders, so it's just the number of suspensions that happened at a school divided by the total enrollment. It doesn't account for the fact that one kid got 7 suspensions. So be that as it may, this is our distribution of out-of-school suspensions. We see from this Moran's I, which is a statistic that measures how clustered or randomly dispersed something is, that this has a bit of a linear relationship, a positive linear relationship, and we can test if that's significant relationship or not by looking, generating 999 permuted distributions, Moran's I distribution. So basically we say that if you take all of the exact same values, shuffle them up and throw them back onto the same polygons on the map, what would the Moran's I be? And you do that 999 times, and that's this histogram we see down here. All of those red lines are the permuted values, and then this green line is our observed value. So we can see that this distribution, this observed distribution of suspension rates is statistically significantly clustered. All right, so principals are in their schools thinking that they have control of everything that goes on in the walls. That's not true, but we would hope that when we're going and doing this research, we're interviewing teachers and we're talking to administrators and doing all this stuff, and the truth is that what is happening outside of the school matters. That's that. Now I can go home. That's the big idea. Anyway, so then we can look at clusters of high and low. I better hurry up. All right. So this is what I came up with as my final regression model. I have a pretty high R squared, but there's a caveat here that climate score does take into consideration some of the OSS, the out-of-school suspension. There wasn't so much overlap there that I had to remove it from my variables. But if I didn't include climate score, then the only thing that was predictive of OSS was the percentage of population that was black. So that's interesting by itself, right? Definitely need to note that. But if I include climate score, then all of these other things that I was interested in looking at start to appear as having some weight on the variation of OSS. So that just means take the adjusted R square with a grain of salt, take the climate score with a grain of salt, but if we control for climate score, then, deep poverty, percentage of residents that have a bachelor's or above, both come up as statistically significant. The percentage of women raising minors is not quite at the 0.05 level, but it is notable. And same with the CDC ratio, which is just the number of I basically took a CDC and divided it. If there was a CDC in the catchment, I divided it by the enrollment at the school. So it was like, here's your portion of CDC, here's your portion, here's what. That's what that ratio is. I'm not saying I did this correctly. Trying to get education researchers interested in doing some spatial analysis. Okay. And, so then I had to take my residuals here and see if there were any spatial dependencies of the residuals. And that if there are, then that means that there's something missing from my model that could be accounted for by location, right? So, and we would probably expect to see this because all my variables are spatially dependent. So here I'm describing how you make a Queen's weights matrix. Does everybody know this? And I'm like preaching to an audience who, okay, good. Now I can say whatever I want. Anyway, so the weights matrix basically says, okay, for any given polygon, which of the other polygons is my neighbor? It's a binary, so we say for all of those in red, it would be a 1 for the one that's in orange, and that's how we can, I used it earlier when we did the Moran's eye, but now I'm just explaining it here. So we do a Moran's eye of the OLS residuals, and that's the Moran's eye. It kind of looks like it's clustered up here, but when we test with 999 permutations, we see that it's actually not statistically significantly clustered, which means I can stop. I don't need to use any spatial regression models. But if I have any time left, do I? I have 2 minutes left, perfect. So in a different project, again, this map, don't judge me, guys. I need to go take some cartography classes. I've really been inspired from this conference. But in this project, I looked at funding by district in Pennsylvania. So here, I'm just looking at the spatial dependencies of the dependent variable. And I have this regression model. Let's see. Oh, yeah, this is of the funding, and here's my regression model, and I'm just showing you this to show you that if you employ some spatial regression models, you can account for a lot of the errors that are actually introduced because you have spatial dependencies. So if I just use regular old OLS, you'll see that I have spatial dependencies. That's that Moran's eye that is statistically significant. But if I use spatial lag, spatial error, or geographically weighted regression, then I can account for the error that is introduced. And that's that. So if you're education researchers, then I will tell you that you should be using spatial analysis in addition to your qualitative and quantitative analysis, because you can use mapping to engage your audience, and because you can use location-specific variables like the ones I used for the OSS project, and also for the, you can also use spatial regression models to, what it says right there. Oh, right, you're recording this, so I should be really professional. I'm done.